Hello everyone. I'm going to talk about the simulator that we use in the lab and how we can use it for simulating DOM code for the dot product that I mentioned before. Let's start by sharing my screen. So I'll go to the Power Tool simulator that is available from the web. So that is HTTPS Simulator.01xz.net. So, and this is a very powerful tool. So we use ARM version 7, and then we are going to use our version system DSOC that is similar to or the same as what we have in the lab. And then we go and it loads the window, and this window has a lot of information to absorb, and I'm not at this time familiar with all of them, so I'm gonna share whatever I've learned so far. So there are different parts of this tool. So the top part would be just running this one, and then it models the devices that are available in the development board that we have. So if you remember from the digital logic course, we had LED, we had switches, we had push button switches, we had 7-segment display, and we have some kind of communication serial ports and so on. So these parts would model those sections of the board. And then in the middle part would be the editor, and the editor in the bottom has editor, disassembly, and the memory. And then the left side, as you see here, there would be registers, which would show you the registers of the ARM. So if you remember from my previous lectures, let's see how we can just update the window. So it's going to be here. Okay. So as you see, there would be some, we are supposed to just change this window. Okay. So now you can see that we have registers. So the register would be the register. Okay, there you go. See. Okay. Yeah, use full screen. That would be better. Yeah. So the register that I have is going to be register R0 to program counter. So R0 to R15, R13, 14, 15, and also the current program status register that I mentioned in my lecture. So let's get started by just loading the program, the dot product that I just explained before. So in order to load that program, we are gonna have the file, and then I'm gonna load it, and then let's see. Okay. So and then that is a dot product. I'm gonna load it. It is shown here. So I increase the window for the editor. For time being, we don't use the devices, so it's going to be here. So then I'm gonna just move it up a little bit. Okay. So you can see, and that is going to be the editor section, and this is going to be the dot product program that I mentioned to you, except I changed it a little bit. So in the example that I show, it has just n was 6, and we have 6 entries for the A vector and B vector. I changed it to 3 in order to show how it works, and I can run it just step by step to show the output and the result of the execution from the registers and so on. Okay, so and then what I'm going to do here is going to be I use the compile and run, and then and after running this one, we get a message compiled succeeded. So that's great. So far, we don't have any problem. So and then here we had in this editor window. Now, when after compiling, then this assembly part would appear. So I can switch back and forth from the editor to this assembly as well. So there would be here you can see that all the registers at the beginning are 0. It might be more not 0, depends on what was previously available there. Since I started, all are cleared. So and then as I mentioned before, the program counter would refer to the address that the current instruction would be fetched and executed, and then it will be updated by adding by 4. So let's say we can also go to the any address by having here. So it's going to be 0. So for example, if I have a 0, then I just enter it, then it will go to the location where the address is 0. By the way, this part has 3 columns. You can see that the left column would be the address. So obviously that is going to be the first address, the first instruction that we have. So if you compare it with the first instruction, you can see that the first instruction is this instruction. So in this instruction, we were supposed to have the address of the A vector loading into the register R0. But that was our initial instruction, which is shown here. But when the assembler just go through this one, it replaces this line with this line. It's interesting that this has a semicolon as a comment, but the original comment format should be followed by a /*. So that was the comment for the simulator. Probably that a comment for the assembly that simulator would be used. Okay. So anyway, so the load R instruction would be used in another addressing mode that I call it relative addressing mode, to refer to the location as compared to the program counter. So the program counter, as you see here, is equal to 0, and that color indicates that this is the current instruction that is going to be fetched by the simulator. So and then that would be after execution of this one, the content of the memory location, which would be related to the program counter. So it's going to be 68 location after, in addition to the program counter. So the reason the CPU, the simulator used this one, because this is called relative addressing mode, because if you copy this part of the code to the another location, you don't want to the address of your data, that code should be working. Okay, so and that address of the data should be relative to the address of the code, and what is the displacement between this address and the data. So in that case, if this was only fixed, then if you move that code to another location, this doesn't work. Anyway, I'll come back to this one later on, but after execution of this one, let's see what will happen. So on in this top, we have the several button. So this button is going to be step by step. this one we are going to have continue to the end, and these two will be similar to this one when we use the subroutine. So, and a step over when we just step over the subroutine, and that would be a step out. And we don't have a subroutine here, so forget about these two. So I'm going to use this one. So I expect that by pushing this one, this button, this instruction would be fetched and executed, and then after that, the program counter would be updated. So obviously we expect that the program counter would be added by 4, and after execution of this instruction, the content of R0 would be the address of the A vector. By the way, let's go below and see what would be the data section of the code. So the data section would start from N. If you see, if you come back here, so these basically this one. So these are the data parts. These 4 lines, and then N followed by A vector, B vector, and dots. Okay, so A vector should contain the value of 3. Sorry, N should contain the value of 3, and A vector each should have a word of the 3 entries. B vector have a word of 3 integers, and these are the numbers are initialized with this vector. So the first entry should be 1, 1, 6. The second entry should be 2, 14, negative 3. So the dot product should be performing 1 times 2 plus 1 times 14 plus 6 times negative 3. Okay, so 1 times 2 is 2, 1 times 14 is 14, 2 plus 14 is 16, and this is going to be negative 18. 2 plus 14 minus 18, so it's going to be minus 2. So I expect that the results of the minus 2 would be stored in the memory location which is defined by dot product. Okay, just keep it in mind. I'll come back this one later when I obtain the answer by the simulator. So now I'll go to this one. So, and then this is the same memory location. So N was initialized to 3. You can see that this is the address of N, which is equal exactly to N. And the content, although it's mentioned as opcode, but since this is data memory, the content is data. So the assembler actually, if you see here, the assembler just decode this opcode by this instruction. This is not the instruction, this is a data. So, and that's initial to 3. And then the A vector, each entry of the A vector is a word, would be stored in the consecutive locations, word locations of the memory. So, and then this location is 30, that is hexadecimal representation. And as I mentioned, 116 was the location that I used here. So it's going to be 116, and each one is a word. So, and that is going to be here 116. And then the next address, each one is a one word which has 32 bits, which is equal to 4 bytes. So you can see that if this address is 30, the next address is 30 plus 4, which is 34. The next address would be 34 plus 4 is 38. The next address would be 38 plus 4. So obviously in the hexadecimal representation, we are going to 312, which is equal to 3C. And again, 312 plus 3C plus 4 is going to be 4C, 4, 4, and so on. And then the B vector, if you come back before, the B vector is initial as a 2, negative 4, 2, 14, negative 3. Okay, so and that would be B vector 2. E is a hexadecimal representation of 14, and the negative 3 in 2's complement representation should be these representations. Okay, so and then the dot product we have it here, and that is going to be, it's always 0, okay, but we could change it, and then that's, since it was 0, so we started from the fresh, so it's 0 here. So let's come back and see what will happen here. So when I, as I mentioned, when